Hello, AP Chemistry. I'm hoping you came back for lesson 1.2 and you haven't left us yet this early in the game. We are going to start talking today about electromagnetic radiation and waves. And actually, if you looked at the lesson, it's broken into three parts. And that's because there are kind of a lot of different things that need to happen when we talk about this concept, the calculations that you have to do, and there's a lot that goes with it. So we'll just take it, one chunk at a time and go from there. The whole idea with this electromagnetic radiation and waves is that we talked a little bit about average atomic mass last time. This time, we're going to be talking about using different types of radiation, not a magnet, to probe deeper into the atom. So the first thing we have to talk about, and that's what 1.2a is going to cover, is what the heck is electromagnetic radiation? So like I said, with average atomic mass, what you do is you use a magnet to discover more about an atom. We take that stream of ionized particles, we use the magnet to bend the stream, and then it gives us information about the mass of the different particles inside of there. You can also use electromagnetic radiation to bombard different elements and compounds, and then you can figure out other information about them. And so that's where we're going from here. Okay. Electromagnetic radiation is actually one of the ways that energy travels through space. So if you think about a vacuum which has nothing in it, electromagnetic radiation is one of the ways that it travels through that energy travels through space. Now, we will spend a lot more time talking about energy later in this course, but for right now, we're just going to kind of take a cursory glance at it and we'll move into way more detail later on. Okay. Now, electromagnetic radiation includes light from the sun, energy in microwaves. So like if you pop something into a microwave and heat it up, that is caused by a microwave, which is a type of electromagnetic radiation. If you've ever broken a bone or gone to the dentist and had to check for cavities, they've given you an x-ray, and an x-ray is a type of electromagnetic radiation. And so is heat from the sun or heat from a fireplace. If you work at a restaurant, you maybe have put food underneath a heat lamp. That is a type of electromagnetic radiation that keeps food warm. So all of these are things that you've very frequently had encounters with, and you maybe just didn't know that they had a special name. Okay. All of them exhibit wave-like properties. So electromagnetic radiation, whether it's a microwave, an X-ray, heat from a fireplace, light from the sun, what happens is they all have wave-like properties. So they go up and they go down and they travel in this wave. And the other thing that they all have in common is that they all travel at the speed of light in a vacuum. And that is going to be important later on when we come and we talk about equations. All right, some general information about waves in case you either haven't heard this before or need a little bit of a refresher. So when we talk about waves generally, like I said, go up and down. You maybe have seen sine waves or cosine waves in your math class. This is kind of that same general idea. And there's some terms that you are going to see that we are going to pay attention to. When we talk about waves, there's amplitude and velocity of propagation. And those are things that are more physics-based and not chemistry-based, so we get to ignore them. But there are two things, the frequency and the wavelength, that are really important. There are also a couple of names for the different parts of them, and we'll get into that in just a second. Okay, so the top of the wave, where the wave is at its highest point in terms of its height, that is called the crest. The lowest point of a wave is called the trough. Like if you think about what you feed barnyard animals in, it's called the trough because they stick their face in and they eat. So that's the lowest part, it's kind of like a little like curvy area in the bottom of the wave. So if I go back here, we've got the crest up here and we've got the trough down here. Now, wavelength, which is represented by the Greek letter lambda. It looks kind of like a Y that got flipped upside down, sort of. So wavelength, which is lambda, is represented in the equation that we're going to use, is measured in meters. So if you think about a meter is, I don't know, probably can't see that proportion, doesn't make sense, but it's, about a little longer than 3 feet. Wavelengths are measured in portions of meters. So is it lots of meters or a little teeny tiny part of a meter? And when you measure the wavelength, you measure it from one point on the wave to the exact identical point on the wave. So if this is the crest, You go down one full cycle of the wave. The length of the wave is going to be the point from the highest point of one wave to the next highest point on the next wave. So that's the wavelength. When you see the wavelength, it should always be in meters when we do calculations for it. It may not always be reported in meters. So keep that in mind, that there's a conversion that we're going to have to deal with, and you will see that in the calculations that we do. So like I said, it's when we do calculations in meters, what they usually measure it in, at least in useful stuff for us, is something called a nanometer. Nanometers, I remember that there are 1 times 10 to the 9th nanometers in 1 meter by remembering the 9. So nano looks kind of like 9, so I think of them as nanometers. So when I'm trying to do a conversion, I remember that there are 1 times 10 to the 9th nanometers, or nanometers as I call them, in 1 meter. And again, when we get to the example, I will show you that calculation. The frequency is measured, the frequency is represented by the Greek letter nu. Now, right here, this might look like a V, but technically it's kind of like a V with an attitude. It's got a little extra little something to it. And the frequency is actually a number that tells you how many waves go past a reference point in a given second. So if here is my reference point, and all of these lights are moving at the speed of light, it is how many waves go past this point in a given second. And that is either called the hertz, it can be called, which is cycles per second or waves per second, or in chemistry, just to keep things easy, they call them seconds to the -1. So you could represent that literally as writing seconds to the -1 power, or you could write 1 over seconds, and both of those are going to be appropriate for calculations. Of course, units are going to be important, and they're going to kind of help guide things, so just make sure that you keep that in mind as we go along. Now, all of the different types of electromagnetic radiation are kind of put together on something called the electromagnetic spectrum. You may have heard of this, you may have not. You probably all experienced something like this, even when you take a look and go outside during a rainstorm and you see a rainbow, because parts of the electromagnetic spectrum are represented. So being a spectrum, what it means is it takes all the different kinds of radiation and it puts them on a scale from one point to the other. So basically it's one extreme to the other. And in this particular one, it is organized by wavelength at the top here and frequency towards the bottom. So on this particular scale, and again, every scale is going to be different, the longer wavelengths are down here and the shorter wavelengths are down here. So if you look, 10 to the 3rd meters, that's like 1,000 meters long. So what that means is one wave is from the crest of one wave to the crest of the next wave is 1,000 meters, which is really, really, really big. Those are classified, if you go anything from 10 to the 3rd meters or longer, all the way to 0.1 meters. So that's 10 centimeters, about the length of a baseball. Those are considered radio waves. So if you tune into a radio station, they are sending out a signal via a radio wave. And when you tune into a specific radio station, you are tuning into the frequency, which is the part down here. So when you are tuning into any given radio station, you are turning into the, technically they're called megahertz, that they broadcast the radio station as, and that's how each station sends its information. They have a different frequency, a different number of waves that go past, which means that their wavelength is different. Once you get into smaller waves, you have microwaves, which you guys are familiar with. Then we get into what we call infrared. Infra means underneath, like infrastructure. So infrared means that it is less or smaller than red, or underneath red. So it's not smaller in terms of its distance, but it is smaller in terms of its frequency. Of all of the light that you can see in the electromagnetic spectrum, interestingly, you can only see this teeny tiny little slice of it, which we call the visible spectrum. And this is where you get your rainbow colors. So you get red, orange, yellow, green, blue, and purple. that show up there. And then those lights are the only things that you can actually see. Once in a blue moon, you can see infrared. Like if you are making a piece of toast, you put the bread into the toaster, and then as you see the element heat up, you see it kind of starts to get warm, and then it turns that orange color. That has to do with, first you feel infrared, because infrared is like heat. And then you start to see the color start to glow. And that's because you're starting to see the electromagnetic radiation transition into the zone that your eyes can actually sense. If you've seen a black light before, a black light hits right at the edge of your visible spectrum and where you're able to actually see different types of electromagnetic radiation. And so that's why it kind of looks a little weird, is because it's starting to get to be the point where your eyes can't actually recognize it. So ultraviolet, ultra means above, which means that it's above violet. And then we get into x-rays. There's kind of two kinds. There's soft x-rays and hard x-rays, and it just has to do with their energy intensity. And then once you get beyond that, you get gamma rays, which are no joke. Those are the things that come off of like nuclear waste that can cause radiation sickness and all that kind of stuff. Something that I kind of want you to pay attention to is that as the wavelengths are longer here, the frequencies are smaller. But in theory, that makes sense because they all travel at the speed of light. So if I have, multiple cars traveling on a highway at the same speed, let's say you have a semi and then you have one of those teeny tiny smart cars. If you have semis back to back to back to back to back, because semis are longer, but they're all traveling at the same speed, fewer semis would go past your point of reference. But if you had all little smart cars or even matchbox cars, because they're traveling at the same speed, but they're shorter, you're going to have more cars go past. And that's the general idea behind frequency, is that as the wave gets smaller, the frequency goes up because there's just more waves that can move past because they're moving the same speed as the long waves. So hopefully that kind of makes sense. Okay, so that's your electromagnetic spectrum. Like I said, we are going to kind of pay attention to the different types of radiation as we go along here because we can use them to poke around on the inside of the atom. So depending on what we have going on, we can actually use these. We can hit them with radio waves. We can hit them with microwaves. We can hit them with ultraviolet radiation or x-rays, and that will lead us to finding information about what's going on inside that particular atom. Now, like I said, your wavelengths and frequencies are tied together. When the wavelength goes up, the frequency goes down. And that is actually because they all travel at the speed of light. In a vacuum, that is a constant. So no matter what type of radiation you have, they're all chugging along at the same speed, which is represented by the lowercase letters c. C is 3.0 times 10 to the 8th meters per second. It's the speed of light. It's really, really fast. On the equation sheet that I handed for you, you'll see it as 2.998 times 10 to the 8th meters per second. That's the speed of light. All I did was I rounded a little bit. You are not going to have to worry. I just used 3 times 10 to the 8th because it's easier. But this equation here is going to be the most important part. If you take the wavelength, lambda, and multiply it by nu, which is the frequency, they always have to give you the speed of light. Sorry, guys, my dog's barking in the background. So no matter what, they always have to equal this constant value. And so that's why they're tethered together. They always, when you multiply them, have to give you 3 times 10 to the 8th meters per second. So when one goes up, the other has to go down. And that's generally how they work. What we're going to do for our first part of this lesson is we're going to practice doing this calculation. So we're going to go through, we're going to check to make sure you remember how to put things into your calculator. I'm even going to go over that. And then we will do a practice calculation. And here is your example. So the example I would like you to try is that a laser developed to use in Blu-ray players has a frequency of 7.41 times 10 to the 14th seconds to the negative 1. What is the wavelength of this light in nanometers? Okay, so what I want you to do is give this a try, and then I will give you the work and the answers in the practice video. All right, good luck.